Section 10.6, conic sections in polar coordinates. Let F be a fixed point, called the focus, and let L be a fixed line, called the directrix in a plane. Let E be a fixed positive number, called the eccentricity. Then the set of all points P in the plane such that the distance from P to F divided by the distance from P to L equals E, that is, the ratio of the distance from F to the distance from L to the constant E, is a conic section. The conic is an ellipse if E is less than 1, a parabola if E is equal to 1, and a hyperbola if E is greater than 1. Looking at our picture, we see that the distance from P to F is R, and the distance from P to L is this distance over here, which we can get by taking the distance d and cutting out r cosine theta. So that means that we have r over d minus r cosine theta equals e. Notice that our picture assumes that the focus is at the origin and that our parabola is an x equals parabola that's negative like that, where the directrix is on the right side of it. So in other cases that'll change cosine to sine or the minus to a plus. But let's just go over this diagram real quick and then we can change it to other cases if we need to. So taking r over d minus r cosine theta, how about we multiply both sides by d minus r cosine theta and then square both sides? So we get r squared equals e squared times d minus r cosine theta squared. And then we can convert to rectangular coordinates and get r squared is x squared plus y squared. E is just a constant, so it stays e squared. And r cosine theta is x, so this becomes d minus x squared. So we can expand that and we get e squared times d squared minus 2dx plus x squared. So what we can do is group together all of our x squared terms. So we get 1 minus e squared times x squared. Group together our x terms, so plus 2 de squared times x. Group together y's, we just have plus y squared. And that equals the constant e squared d squared. So if we divide through by 1 minus e squared, then we can complete the square and we'll end up with x plus e squared d over 1 minus e squared plus y squared over 1 minus e squared equals e squared d squared over 1 minus e squared squared. Notice all we did was we divided by 1 minus e squared, and then we have to add half of this middle term squared to both sides, so that means we add de squared to both sides, and when we do that, e squared d squared becomes e squared d squared over 1 minus e squared squared when we find a common denominator there. So if you just pretend that you can actually make sense of all of these weird constants e and d and e squared d and all that, then this is just x plus something squared, x plus some constant squared, plus y squared over some constant equals some constant. So what you can do is you can divide the entire equation by this constant on the right side, and then it'll equal 1. So you'll have x plus something squared over something plus y squared over something equals 1, which is definitely a conic section, assuming that e is not 1, of course. If e is equal to 1, then this just becomes pf over pl equals 1. So then you just have this times this, this divided by this, equaling 1, so they equal each other. When the distance from a point to a focus equals the distance to the directrix, that's literally a parabola. So assuming that it's not equal to 1, then we get this, which is an ellipse if e is negative. If e is bigger than 1, then this becomes negative. So this becomes negative, so we get a hyperbola. So it kind of converts out, as long as you're careful with all your constants. Notice that in order to make this thing a ellipse or a parabola or whatever, we want it in standard form, we set it equal to 1, so then we would have to divide this thing and this thing by this thing. So that means that this thing is a squared, because that's what we would put underneath the x term. And this thing, well, this thing divided by this thing is b squared, so we can just forget about one of those for b squared. Notice that we have r equals ed over 1 plus or minus e cosine theta, and r equals ed over 1 plus or minus e sine theta. We just get that from this thing right over here. We multiply through both sides by d minus r cosine theta, and then we distribute the e, we group together the r's, and we just solve for r, and we get this. However, we have to account for other cases besides our picture, where we just have the directrix on the right side. If we have the directrix on the left side, then our plus becomes a minus. And if we have it on the top, then it becomes sine. If we have it underneath, it becomes minus with sine. Notice that even though there's a minus sign over there, it disappears when you multiply by the other side and then move the r cosine theta term to the left side to group it together with r's. The minus becomes a plus, which is why we end up with a plus over there where the directrix is on the right. So you have to be slightly careful when deriving these equations right over here with the signs. So let's do an example. We'll find a polar equation for a parabola that has its focus at the origin and whose directrix is the line y equals -6. So we're given that e is equal to 1. And notice that the directrix is y equals -6, so it's underneath the focus. So that's this case right over here. So if y is equal to -d, that means that d must be equal to 6. So we have r equal to e times d, that's 6 times 1, which is 6, over 1 minus e sine theta, so 1 minus 1 sine theta. A conic is given by the polar equation r equals 10 over 3 minus 2 cosine theta. Let's find the eccentricity, identify the conic, locate the directrix, and sketch it. So we have r equal to 10 over 3 over 1 minus 2/3 cosine theta. If we put this thing in standard form, we just divide the top and bottom by 3. So that means that now we know our eccentricity is 2/3. And since our eccentricity is less than 1, this implies that our conic is an ellipse. So now the numerator is e times d, which is 10/3. So that tells us that we can get d by itself by taking 10/3 and dividing by e. And that means it's 10/3 divided by 1/2, which is 5. So our directrix, well, remember this is cosine, so this is an x equals directrix. So our directrix is at x equals -5, because in this case, we're negative for our directrix. So all we need to do now is figure out where our vertices are. Well, our vertices are along the x-axis because the directrix is an x equals line. So that means that we should know where theta is 0 and where theta is pi. That'll put us on the x-axis. So theta is 0. If we plug that in, then we get 10 over 3 minus 2 times cosine 0, which is 1. So 10 over 3 minus 2 is just 10 over 1. So that means that r is 10. And similarly, if we plug in theta equals pi, we get 10 over 3 minus minus 2, so that's 10 over 5, which is 2. So we can draw this now. So we put our focus at the origin. And we put one vertex at 10, 0. And we put the other vertex at 2 pi because we're in polar coordinates. And our directrix is at x equals minus 5. So we get this rough looking ellipse. I just missed it. Not happy with that. I should have been more careful to put that on the inside, but that's okay. So that's our ellipse, r equals 10 over 3 minus 2 cosine theta. Let's sketch the conic r equals 12 over 2 plus 4 sine theta. So again, we'll divide the top and bottom to put this in standard form. So we get r equals 6 over 1 plus 2 sine theta as long as we divide by 2. Or just divide by whatever that is to get 1 over there. So eccentricity is 2. So that means that we're looking at eccentricity bigger than 1, so that's a hyperbola. So we still have E times D equals 6, which means that D is equal to 3. And we have a plus over here, so our directrix is positive y equals, because we have sine, so it's y equals, it's vertical. So our directrix is y equals 3. Theta, let's look for where we intersect our y-axis now. So when theta is pi over 2, we'll hit the y-axis. Well, that means that r will be 2. And when theta is 3 pi over 2, we'll hit the y-axis again. So that's when r is equal to minus 6. Since this is a hyperbola, let's try to figure out what the asymptotes would be. So let's look at what happens to r as it goes to plus or minus infinity. Well, that will happen when the denominator goes to 0. So that means that we're looking for when 1 plus 2 sine theta goes to 0 from the right or from the left. So we can get 2 asymptotes. Well, that happens when this thing goes to 0, so that's when sine theta goes to minus 1/2. Well, sine theta goes to minus 1/2 at theta equals 7 pi over 6 and theta equals 11 pi over 6. So that means that our asymptotes must be parallel to those lines. So let's try drawing this now. So I have vertices at radius 2, angle pi over 2. So here's one of them. And my other one is at negative 6, 3 pi over 2, which is the same as flipping around, making r positive and going to pi over 2. So I'll put 6 pi over 2 over here, which is the same as negative 6 3 pi over 2. And I've got my asymptotes halfway between those guys. So let's try drawing those. Something like that. Okay, so those are my asymptotes parallel to theta equals 7 pi over 6 and theta equals 11 pi over 6. And at this point, oh, how about we put in our directrix too? So our directrix will be the line y equals 3. And our focus is the origin, of course, because all of our polar conics have focused the origin. Okay, so now I think we can connect this. Well, it would be a little bit better if I went a little bit closer to my asymptote. Something like that. And on the bottom. We could actually figure out where it intersects in the x-axis pretty easily, because these points would have to be when theta is 0 and theta is pi. So notice that you can plug in 0 for theta, and you just get 12 over 2, so that's 6. And then you can use symmetry to see that this is going to be 6 pi, or just plug in pi and see that, again, it's going to be 6. So that's our hyperbola, r equals 12 over 2 plus 4 sine theta. When we plot conic sections in Cartesian coordinates, we often translate them, move them up and down, left, right. When we plot conics in polar coordinates, it makes it easier for us to rotate conics around. Because if we have an angle of pi over 4, we could just take theta minus pi over 4, and then we would get our rotation. So instead of r equals 10 over 3 minus 2 cosine theta, which we did in example 2, we can rotate by pi over 4 by writing r equals 10 over 3 minus 2 cosine theta minus pi over 4. And then if we're to graph this, then let's say I'm using a different color for our original ellipse. So here's our original ellipse. It was at 10 and 2. And let's see if I can manage to draw this thing. So then we're gonna rotate this. So this was the equation r equals 10 over 3 minus 2 cosine theta. So now we'll rotate that and get our ellipse 10 over 3 minus 2 cosine theta minus pi over 4. So our focus should stay the same because we're rotating about the focus. So it should look something roughly like this. And then here's still our focus at 0, 0, the origin. And here's our rotated ellipse, r equals 10 over 3 minus 2 times the cosine of theta minus pi over 4. The polar equation of an ellipse with focus at the origin, semi-major axis A, eccentricity E, and directrix x equals d can be written in this form. So you might be saying, well, what happened to the E times d in the numerator? Well, remember that we said that our equation for an ellipse in Cartesian coordinates would be this guy. So we can get what a is by dividing both sides by this. This is a squared. So e squared d squared over 1 minus e squared squared is a squared. So let's use that. So we have a squared equals e squared d squared over 1 minus e squared squared. So all we have to do is solve for e times d. So we multiply both sides by 1 minus e squared squared. We take the square root. We get that e times d is a times 1 minus e squared, which is that. So now the positions of a planet that are closest to and farthest from the sun are called its perihelion and aphelion, respectively, and correspond to the vertices of the ellipse in our figure. So the distances from the sun to the perihelion and aphelion are called the perihelion distance and aphelion distance. Then we have the perihelion distance from the planet to the sun as a times 1 minus e, and the perihelion distance, and the aphelion distance is a times 1 plus e. So we just take a look at our equation, a times 1 minus e squared over 1 plus e times the cosine theta, but we plug in theta equals 0, because that's where perihelion would be. And when we plug in theta equals 0, we just get 1 plus e in the bottom, so that cancels with one of the 1 plus e's on top, and we end up with r equals a times 1 minus e. If we plug in theta equals pi, then we get the aphelion, and then in that case the 1 minus e will cancel and just leave you with 1 plus e. Let's find an approximate polar equation for the elliptical orbit of the Earth around the Sun at one focus, given that the eccentricity is about 0.017 and the length of the major axis is about 2.99 times 10 to the 8th kilometers. So if we have the length of the major axis as that, then that means that that's what 2a is equal to. So we have 2a equals 2.99 times 10 to the 8th. So that means that a by itself is equal to 1.495 times 10 to the 8th. So we're given the eccentricity, E, is 0.017, and we can write R equals a times 1 minus e squared over 1 plus e cosine theta. So that's just going to be 1.495 times 10 to the 8th times 1 minus 0.017 squared over 1 plus 0.017 cosine theta. And because this is really tiny, we can just approximate R by forgetting about that term altogether and just writing 1.49 times 10 to the 8th over 1 plus 0.017 cosine theta. So that's an approximate polar equation for the elliptical orbit of the Earth around the Sun. Let's now find the distance from the Earth to the Sun at perihelion and at aphelion. So first let's do perihelion. Well, then we have a times 1 minus e. So that's going to be approximately 1.495 times 10 to the 8th times 1 minus 0.017, which is about 1.47 times 10 to the 8th kilometers. Now let's do aphelion. So that's going to be a times 1 plus e, which is about 1.495 times 10 to the 8th times 1 plus 0.017, which is about 1.52 times 10 to the 8th kilometers.